4.3 and 4.4. Okay, the first property is about increasing, decreasing. So I'm going to put the note here. Recall the f prime of x is the slope, right? It's the slope of the graph. Actually, the slope of the tangent. Now, to identify the slope, the function increasing, decreasing, slope positive, right? Slope positive or the m positive, the graph increasing. The m negative, the graph is decreasing. I'm sure you guys are familiar with this concept. So in order to use the derivative form, we just come up with the definition of f increasing, decreasing as for the f prime as a slope, right? F prime greater than 0, then the f of x is increasing. F prime of x less than 0, the f of x is decreasing, just this straightforward way. And for the nonlinear graph, you're going to have the graph that up and down, up and down. It's not a straight line as what you used to in the previous math course. So then going to be the intervals that has different behavior. Maybe some interval, the graph increasing, some interval, the graph is decreasing. So we're going to use the derivative in order to identify the interval of increase, decrease. Okay, and how to identify those? You're gonna need the critical point. So you're gonna find the critical point as you did back in section 4.1 to find the critical point as the breaking point. That means you're gonna look for the derivative at some point that the derivative is 0 or the derivative is undefined. Gonna be two cases unless you are working on the polynomial function. For the polynomial, everything is defined, so you don't have to worry about the case of the undefined thing. The case of undefined comes when you have the rational function form that the denominator could be 0, right? Or the natural log or the square root. The first derivative test is the test to find the local max, local min. Local max, local min. How do you use the first derivative test? So you're going to have to find the critical point, okay, the critical point. And the critical point, which is from either f prime equals 0 or f prime is undefined, the first derivative test said at the point C or at the critical point C, okay, if this is the first derivative, okay, if the sign change from positive to negative, it will give you like think about the nature of the graph. If prime positive, that means the graph is increasing, right? Increasing. And then if prime negative, the graph is decreasing. So at the point C is a point of changing the sign from positive to negative. The point C or F at C is local. Think about the nature of going up and coming back down. That point gonna be a local maximum, be local max. Okay. And another case, point C, the F prime, use the real number line as a tool to identify the local max, local min. At the critical point C, so x equals C here. So if the sign change from negative to positive, again, negative slope, the graph decreasing, positive slope, the graph increasing. That means by the first derivative test, FC is a local minimum. It's this straightforward. Another case that you have the point C as a critical point, but the sign no change. If it's increasing, pause increasing, or the other way, like negative, negative, the graph decreasing and then decreasing again. So for this case, we can say like no local. So FC, we can say FC is neither local max nor min. Okay, because C is just the resting point from increasing and then keep going to increasing again or decreasing, stop decreasing again. Okay, so this is about the first derivative test. Okay, the first derivative test using the critical point. That means you're going to have to find the critical point whatever how many points that you have, you might have one, you might have two, you might have none. So depends on the function that you use in the problem. Okay, that's the first derivative test. Questions? All right, and then for the case that we find the inflection point and the concave up, concave down. So next up again. So the inflection point and then concave up down. Okay, the definition of concave up, concave down. The graph behave like for the concave up. Okay, we're gonna use the second derivative to identify it. Concave up, that means the rate of change of the derivative is positive. Sound confusing, I know. So we use a second derivative, f double prime greater than 0, concave up, f double prime less than 0, concave down. Okay, concave down. And the f double prime is the prime of the first derivative. So that means the rate of change of the f prime. Okay, for example, you have the case that the graph go this way. Okay, go this way. And then you can use the tangent line. Pretend like you you have a pen, a pencil, and you go across, I mean not go across, go along the curve, and you observe the rate of change of the slope. See the first one here, I call this is M1, and this is M2, and this is M3. Think about these M's numbers. So M1 steeper and not as steep, not as steep, right? It looks like the rate of change of the slope is decreasing. So this is a case of concave down, concave down, because the slope is not rising at it as you go along the curve. Another case, if you have the case like the graph is, for example, one side of the parabola, and same way, I'm gonna use a tangent line and go along the curve. Okay, go along the curve, and this is my M1, my M2, my M3, and so forth. And looks like the M1 is less than M2, less than M3 as I go along the curve. Not like the concave down case. The concave down is the M1 less than M2. No, another way, sorry. So, so for the case on the right graph here, as the slope is rising, is increasing. So this case gonna be concave up portion of the graph. Okay, so you can use the graph to identify the rate. You use the graph to identify the concave up, concave down interval, or use the second derivative to identify the interval of concave up, concave down. Okay, for the graphical way, the original graph or the graph of the function will be for the concave up. The graph will be above your tangent line. For the concave down, the graph going to be below your tangent line. Okay, concave down below, concave up above. Use your tangent line as the guideline to go along the curve, whether it concave up or concave down. For the analytical way, you find the second derivative. If the sign positive, the graph concave up. If the sign negative, concave down. And I use the notation, I use the symbolic, I mean the emoji like the f double prime greater than 0, I'm happy. Less than 0, I'm not happy. When I use this way, this is my concave up symbol, and this is my concave down symbol. I'm happy because my F double prime positive. I'm not happy when the F double prime is negative. And this kind of helped me um, to see the, to get to the point quicker than just memorizing too many things. Okay, just a quick tip. All right, and then the next part is about the inflection point. For the inflection point, let me find the pen. For the inflection point, you're gonna find the F double prime at the point C. It could be 0, or the F double prime at point C is undefined. Same way that you use, or the process that you did with the critical value, but you just work on the second derivative. Okay, once you get the point C, now you're gonna, it should, yeah, C is fine for this one. So inflection point for that number, same thing, you draw the real number line, but this one is about the second derivative. At that point, I'm going to use the different one. So I'm going to use x instead of the c, because c we use for the critical point. So for the x here, if the sign positive, remember, am I happy or not happy for the sign positive? I'm happy, right? I'm happy. If the sign negative, I'm not happy. So the happy portion here is my concave up, and my not happy is my concave down interval. And if the sign changing from positive to negative or negative to positive, so that point is called the point of inflection or the inflection point. So X is an inflection point. Some textbook they use the term like POI, which is the point of inflection. Just in case you use more more than one book as a reference. POI, or the point of inflection. If the sign change, yes. If the sign doesn't change, so we don't call that as an inflection point. Okay. And now, how do we use the second derivative test? The name again, the second derivative test. Use a second derivative to locate the local max min. The same purpose as the first derivative test. But this one is kind of the extra step to get to the point as what we are looking for as a local max, local min. How do we use the second derivative test? You're gonna start with the critical number first. Okay. So number one, you have to find the critical point, which is the point C. Okay, the point C from, as we did before, from f prime equals 0 or f prime at c undefined. Okay, start with the critical point, and then step number 2, you're gonna find the second derivative. Find the second derivative, and then draw the real number line. The real number line. If the point c, so for example, if this is a concave, this is the second derivative line. Okay, and if the point c is over here, I write it as a C1, right? Over here as a C2. If the critical point C1 is in the interval of concave up, which is the side positive of the second derivative test, second derivative, and the other one as a concave down interval, which is the negative sign. If the point C is in the concave up, I'm gonna use the same notation that, or the icon that I used before, concave up, right? I'm happy. Concave down, I'm not happy. My C1 is in a concave up, so C1 gonna be the local minimum. And my C2, which is in the interval concave down, my icon is not happy. I see the bump up here. So my C2 is my local maximum.